Good afternoon, everyone. Today we are going to explore several challenging concepts from reservoir fluid properties. Each of you has identified your own pain point and will use different active learning methods to understand them together. So let's begin. Who wants to start?
Excuse me, sir, but I do not understand the standing cuts correlation graph. The curves looks a bit confusing. Can you explain it to me?
That's completely normal. Let's break it down using the Feynman method. Think of the Z as how real the gas behaves. If Z is equals to 1, which means it is perfect ideal gas. If the Z factor is less than 1, which means the attractive force dominates. If Z factor is larger than 1, which means the repulsive force dominates. Okay, next, the standing cuts chart uses the pseudo-reduced temperature to locate and find the Z factor. First, the steps are you compute the reduced temperature, TR, using this formula, which is the temperature over the critical temperature and same as reduced pressure. After that, you move horizontally to your reduced pressure and you go up to the chart and you locate your reduced temperature, and that intersection point you can find your Z factor.
So this is a standing and cuts chart, and as you can see, the x-axis is the pseudo-reduced pressure and the y-axis is the compressibility factor, and inside the chart there is the pseudo-reduced temperature, and you find your pseudo-reduced pressure and you go up and you find your pseudo-reduced temperature and you go left and you will find your Z factor.
Okay, Mia, can you teach me back again to me?
So, first find the reduced temperature and the reduced pressure, and we find the curve of it, and we find the intersection, and thus we get the Z factor.
Exactly, that's the Feynman technique. If you can teach it, you understand it.
Yeah. I struggle using the standing and cuts correlation graph to predict the fluid density, especially the pseudo-density steps.
Okay, let's start with a simple example. Let's say we have 10% of C1, 5% of C2, and 85% of C3 plus. Normally for questions like this, they will give the mole fraction or the percentage of the mole, and you need to put it down as mole fraction. The C3 plus, it could be N-butane and hexane or any other components down below. And you need to count the density of C3 plus using additive volume as your first step. Normally they will give you a table and you need to write down all the molecular weight for each component, and you need to use the data to solve as a volume, density, weight, and so on, yada yada yada. And those data will be given in a table itself.
Just to add on, there is a special case for C7 plus component. The molecular weight of heptane plus will be given and its specific gravity as well, and you need to use this data to find the pseudocritical temperature.
And next step, you need to determine the weight of C1 in C1 plus and the weight of C2 in C2 plus. By having this data, you can use the standing and cuts pseudodensity chart to find the mixture pseudodensity. Okay, Yasmin, can you handle step 1?
I think I can, but we will start calculate the C3 plus density using additive volume of its components, right?
Exactly, that is practice-based learning. You solve while you learn. Well done, Yasmin.
Sorry, but I don't get the recommendation for the composition are unknown.
Okay, before the formulas, let's understand the concept. When reservoir gas moves up to the surface, the heavy components of the gas will drop out at liquids. As this happens, the surface gas is lighter than the reservoir gas.
And for dry gas, as you can see from the slide, no liquid condenses from the gas as it moves from reservoir to surface. So the volume of the gas will expand from reservoir conditions to standard conditions, even though they have the same compositions and specific gravity.
So we need to rebuild it from the separator gas, stock tank gas, and stock tank fluid. And if the composition is unknown, we use production data to estimate the gas gravity using correlations like VEQ and AGP.
This is the example of correlations of left VEQ and right AGP.
Mueez, can you restate the core idea?
So basically, first of all, we need to reconstruct the reservoir gas by combining the surface fluid, and then if we don't have the composition, we need to use the correlation.
Perfect, that's concept first learning.
I am confused about solution gas ratio above and below bubble point.
Let's do think, pair, share. Think, if the reservoir pressure is higher than the bubble point, what happens to the gas?
No gas come out of the solution?
Correct, so the RF stays constant. The oil is undersaturated. Now pair that with this. What happens when the pressure drops below bubble point?
Gas evolve out, so RS will decrease.
Exactly, that's think, pair, share method. Great work everyone! Today we clarified the Z factor from standing in cards by using the Feynman technique. We also learned density prediction using standing in cards from practice-based learning method. We also learned recombinations of composition of unknown using the concept first learning, and also the G or R solution using think, pair, and share method. Thank you all. See you guys in the next class. Thank you.
But before that, let us share some fun facts about what we have learned so far.
The Z factor shows how non-ideal a gas is, meaning gas in reservoir almost never behave perfectly. Oil can flow like a liquid, but also behave like a gas underground depending on pressure and temperature. Some reservoirs contain invisible liquids, which is known as the gas that turns into the liquid when it reaches the surface. A drop in pressure can suddenly cause a gas to come out of the oil, similar to opening a soda bottle.
Deep underground, fluids exist under extreme conditions that can reach temperatures hotter than boiling water. Not all oil is liquid underground. Some can be thick like honey or even nearly solid. Gas expansions in pipelines can cause cooling effects, which is why temperature changes matter in production. Engineers sometimes rely on correlations instead of experiments because reservoir conditions are too extreme to replicate easily.
That's all for now. Thank you for your time and we hope you have a wonderful day.